Africa has some of the world's strongest solar and wind resources, large areas of available land, growing industrial demand, and access to major shipping routes. On paper, the continent appears ideally positioned to produce green hydrogen. But renewable resources alone do not create bankable projects. Before an electrolyzer is installed, developers must study the site, electricity supply, water, technology, customers, environmental impacts, infrastructure, and financial viability. All of this costs money before the project generates revenue. Namibia offers an important example of how that early gap can be addressed through government cooperation, strategic partnerships, feasibility work, grant funding, and a manageable demonstration project. The project is Cleanergy Solutions Namibia's integrated green hydrogen production and refueling facility near Walvis Bay. It was developed by Cleanergy Solutions Namibia, originally established through a partnership between Namibia's Oathaver and List Group and Belgium-based CMB.Tech. The project was designed around a 10-hectare solar park, a 5-megawatt proton exchange membrane electrolyzer, a 5-megawatt-hour battery, hydrogen storage, and refueling infrastructure. Rather than starting with a massive export facility, the sponsors chose a smaller integrated demonstration project that could test hydrogen production, storage, transport, refueling, training, and practical applications within Namibia. The story did not begin when construction equipment arrived at the site. It began when Namibia and Germany created a framework for cooperation on renewable energy and green hydrogen. Their joint communique of intent called for feasibility studies before joint pilot projects were implemented. These studies were intended to evaluate Namibia's hydrogen production potential, economic and environmental risks, water and desalination, available technologies, supply chain barriers, transportation, trade, and possible demand in Namibia, Germany, and other markets. This meant the pilot projects were not supposed to begin with equipment procurement. They were intended to emerge from a structured process of research, analysis, capacity building, and evidence-based project preparation. A green hydrogen feasibility study must answer far more than whether electrolysis works. The technology is already understood. The real question is whether a complete project can operate reliably at a particular location and sell hydrogen at a viable price. Developers must investigate renewable power production, plant utilization, water availability, equipment sizing, compression, storage, transportation, safety, permitting, environmental impacts, and customer demand. They must also estimate capital expenditure, operating expenditure, hydrogen production, revenue, financing costs, and project risk. Without this work, investors are being asked to finance assumptions. Feasibility turns those assumptions into documented evidence and identifies which problems must be solved before capital can be committed. The difficulty is that serious feasibility work can be expensive. Engineers, environmental consultants, lawyers, market specialists, and financial advisors must be paid before there is a constructed plant or operating revenue. Yet banks and major investors usually want this work completed before considering construction finance. This creates the early-stage funding paradox. The developer needs money to prove the project, but financiers want proof before providing money. Many African clean energy projects become trapped at this stage. They may have excellent resources and ambitious sponsors, but they cannot fund the technical package needed to become investable. Namibia's approach was to place feasibility work, research, pilot projects, and skills development inside a larger government-to-government cooperation framework. The first lesson is that donors rarely want to fund an isolated idea with no capable project owner. Cleanergy combined a major Namibian business group with an international company experienced in hydrogen technology and applications. The local partner brought knowledge of Namibia, local institutions, business conditions, and implementation. The international partner brought hydrogen engineering, equipment knowledge, and experience connecting hydrogen production to practical uses. Other African developers can follow this structure by combining a credible local sponsor with a strategic technology, industrial, engineering, or offtake partner. The partnership must be genuine. Each organization should have a defined role, provide resources, accept responsibility, and demonstrate that it can help move the project from study to implementation. A project becomes more credible when the hydrogen has a defined purpose. Cleanergy was not presented only as a facility that would produce hydrogen and search for customers later. Its concept included hydrogen production, storage, refueling, mobility applications, training, and technology demonstration. The integrated facility has subsequently supported applications, including dual-fuel trucks, tractors, and off-grid hydrogen generator sets. This creates a direct connection between the plant and the equipment that may consume its output. Other African developers should begin with a specific customer or application. Fertilizer production, mining trucks, port equipment, industrial heat, a refinery, a bus fleet, or remote power. A named use case gives a feasibility study something concrete to evaluate. Before applying for major funding, developers should complete an initial site screening exercise. The project team must determine whether proposed land is available, accessible, environmentally acceptable, and close enough to electricity, water, roads, customers, or export infrastructure. A strong concept note should include a preliminary map, site control status, renewable resource information, water options, infrastructure connections, and potential environmental constraints. This is not yet a complete feasibility study, but it shows that the concept is tied to a real location. Donors and strategic partners are more likely to support a defined project than a general proposal based only on the claim that a country has strong sun or wind. A fundable study should be divided into clear work packages. The renewable energy study evaluates solar or wind output and the hourly power profile. The technical study compares electrolyzers and sizes the balance of plant. The water study assesses supply, treatment cost, and environmental impact. The market study identifies users and possible offtake structures. Environmental and social work evaluates biodiversity, land, communities, safety, and permitting. The financial model calculates capital costs, operating expenses, hydrogen output, selling price, levelized cost, return, and sensitivities. The final implementation plan defines engineering, procurement, construction, training, financing, and expansion. Each work package must produce a decision quality deliverable rather than a general discussion. A feasibility report should not end by simply stating that green hydrogen is promising. It should lead to a clear decision. The project may proceed only if specific conditions are met, require redesign, or stop. Decision gates can include minimum renewable yield, maximum water cost, confirmed environmental clearance, an acceptable hydrogen production cost, a credible customer, or minimum grant contribution. This is important because donors are not funding research for its own sake. They want the study to prepare a credible pilot or commercial project. The proposal should therefore explain exactly how the study results will support an investment decision, permitting process, financing application, or procurement program. The Namibian model benefited from formal cooperation between the Namibian and German governments. The joint communique created a recognized framework for feasibility studies, research, pilot projects, education, and technology cooperation. That government alignment gave the program strategic legitimacy and connected individual projects to national development goals. African developers should therefore engage the appropriate ministries before approaching international donors. The project should demonstrate alignment with national energy policy, climate commitments, industrial development, job creation, local value addition, and skills development. Government endorsement does not mean the government must own the project. It means the project fits within a broader national strategy and has a clearer pathway through regulations, institutions, and international cooperation. Developers should not send the same proposal to every donor. A research ministry may support technical studies, scientific cooperation, and skills. A climate fund may focus on emissions reductions and development impact. A development bank may fund project preparation, infrastructure, or concessional debt. An export credit institution may support equipment supplied by companies from its home country. A strategic industrial partner may finance the work because it wants future hydrogen supply. The Cleanergy program received German federal support through the German-Namibian partnership. The broader lesson is that developers must match the project's needs with the funder's mandate instead of simply searching for any organization offering money. The funding structure also included SASSCAL, the Southern African Science Service Center for Climate Change and Adaptive Land Management. SASSCAL has supported program implementation, coordination, monitoring, research, skills development, and cooperation between institutions. This structure is important because an international donor may not want to transfer a large grant directly to a new project developer without oversight. An implementing institution can evaluate proposals, administer agreements, verify expenditures, review milestones, coordinate stakeholders, and report progress. Other African countries could use a national development agency, regional research institution, university consortium, development bank, or specialist project preparation facility to play this role. Independent administration can increase donor confidence and strengthen accountability. Public records describe Cleanergy's award as a JCOI/PTX grant supporting the hydrogen pilot plant and refueling station. Oathaver and List reported that Germany's Federal Research Ministry awarded 30 million euros across 4 Namibian pilot projects, including Cleanergy. ONL's 2024 annual report states that Cleanergy concluded a grant contract worth approximately 10.782 million euros, administered through SASSCAL. CMB.tech has separately referred to a German federal grant of approximately 10.2 million euros. The public record does not isolate a specific amount exclusively for a standalone Cleanergy feasibility study report. The safest conclusion is that German funding supported the wider package of preparation, research, demonstration, training, and pilot implementation. Grant funding should not replace developer commitment. A credible sponsor should contribute staff time, management, local development work, technical resources, equity, land arrangements, or other project costs. This demonstrates that the developer is not using public money to test an idea, it is unwilling to support itself. Cleanergy's project was backed by established corporate sponsors and was initially announced as an approximately $18 million investment. The public grant reduced first-mover risk, but the project also depended on sponsor capability and involvement. Other developers should clearly show what the grant will fund, what the sponsors will provide, and how later phases will be financed. This creates a more credible path from public support to commercial investment. The scale of the first project matters. Beginning with a multi-billion-dollar export facility can create overwhelming requirements for renewable power, ports, desalination, pipelines, customers, and financing. Cleanergy instead developed an integrated demonstration facility using a 5-megawatt electrolyzer. That scale was large enough to generate meaningful operating data, but small enough to function as a practical first phase. Other developers can apply the same principle through a 1 to 10 megawatt project tied to one mine, fertilizer plant, transport fleet, port, industrial customer, or remote energy application. The pilot should be designed to answer questions required for expansion, including system performance, maintenance, customer acceptance, safety, hydrogen costs, and workforce capability. Environmental work must begin before the project is fully designed. The study should screen biodiversity, land use, water extraction, wastewater, brine disposal, noise, traffic, hazardous materials, hydrogen safety, community impacts, and cumulative development pressure. Findings may change the project location, layout, technology, cost, or schedule. In water-scarce regions, water supply and desalination can become central investment questions rather than minor technical details. The German-Namibian Cooperation Agreement specifically identified desalination technologies, marine biodiversity, ecological impacts, and supply chain feasibility as study areas. Other African projects should budget for environmental and social studies as part of project preparation, not treat them as paperwork completed after engineering decisions are made. Hydrogen production is not bankable without demand. The feasibility study must identify who will purchase a hydrogen, how much they need, what fuel it replaces, what conversion equipment is required, and what price they may be able to pay. A letter of interest is useful, but it is not the same as a long-term offtake agreement. Developers should progress from market interviews to letters of intent, memoranda of understanding, pilot supply agreements, and eventually binding contracts. Cleanergy's integrated refueling and demonstration approach allowed local hydrogen applications to be tested rather than relying only on a distant future export market. Other African developers should use domestic demand to create early operating experience, even when export remains the long-term objective. Hydrogen infrastructure requires trained engineers, operators, maintenance technicians, safety personnel, regulators, emergency responders, and laboratory specialists. A technically sound project may still fail if these capabilities are unavailable locally. Cleanergy's model incorporated a hydrogen academy and continued training, testing, and research activities. Under Phase 2, additional funding supports training, laboratories, vehicle applications, generators, university infrastructure, and studies on solar panel cleaning and degradation in desert conditions. This shows how a demonstration project can generate knowledge for the wider industry, rather than operating as an isolated plant. Other African developers should include universities, technical colleges, laboratories, apprenticeships, and safety training directly within the funding proposal. The pilot's greatest value may not be the first kilograms of hydrogen it produces. Its most valuable output may be data. Developers need actual information on renewable power output, electrolyzer efficiency, battery performance, water consumption, plant availability, maintenance, compression losses, refueling time, customer behavior, and operating cost. This evidence can improve the next feasibility study and reduce uncertainty for larger investors. Phase 2 of Cleanergy includes research into solar panel cleaning and performance degradation under desert conditions, an example of operational learning that could influence future renewable hydrogen projects in Namibia and similar environments. The African model should therefore treat every pilot as a structured data generation platform for commercial expansion. A demonstration grant is not the final financing model. Once the pilot produces credible data, the developer must prepare for larger capital sources. These may include sponsor equity, strategic investors, concessional debt, development finance guarantees, export credit, commercial loans, and long-term offtake-backed finance. The grant absorbs risks that conventional lenders are unwilling to take at the beginning. The pilot then produces evidence that can attract more commercially oriented capital. Developers should design this transition before accepting the grant. The proposal should explain what financing is expected after feasibility, after the pilot investment decision, after commissioning, and after performance has been demonstrated. Without that pathway, a successful pilot may remain permanently small. The model can be summarized as a sequence. First, identify a real local problem that hydrogen may solve. Second, establish a credible local project owner. Third, secure an experienced technical or industrial partner. Fourth, define the site, customer, technology, and study scope. Fifth, obtain national government alignment. Sixth, approach a bilateral donor, climate fund, development institution, or project preparation facility. Seventh, place grant administration under a capable implementing organization. Eighth, complete feasibility, environmental, market, and financial work. Ninth, construct a manageable pilot. 10th, collect operational data. Finally, use the evidence to attract larger-scale commercial financing. The technology may vary, but the development sequence can be replicated. The application should not simply request money for green hydrogen. It should request support for specific decisions and deliverables. These can include a bankable feasibility study, renewable resource assessment, water study, front-end engineering, environmental and social assessment, market and offtake analysis, financial model, legal and regulatory review, workforce plan, permitting roadmap, and pilot implementation package. The proposal should state the site, potential customer, study budget, schedule, sponsor contribution, implementing partners, and decision criteria. It should explain what happens after the study and how the project will move toward investment. This transforms a grant request from a broad ambition into a structured project preparation program. Many developers begin by selecting an electrolyzer before confirming the customer, electricity profile, water source, or financing route. Others seek grant funding without a credible local partner, define site, sponsor contribution, or government alignment. Some produce reports that describe hydrogen potential, but do not contain decision quality engineering or finance. Others design export megaprojects before approving a smaller domestic use case. The Namibia model suggests a more disciplined approach. Build a consortium, define the application, fund the studies, manage the grant transparently, construct a pilot, train local people, generate operating data, and expand only after the evidence supports expansion. The project is developed step by step rather than announced all at once. The most important lesson is not that every African country should build the same 5-megawatt plant. The lesson is that successful hydrogen development requires an institutional and financial system around technology. Cleanergy emerged through local ownership, international expertise, government cooperation, structured feasibility work, German grant support, SASSCAL administration, an integrated demonstration facility, practical applications, and skills development. Other African developers can follow this model by making the first project smaller, more focused, more transparent, and directly connected to a customer. Africa does not need to wait for billions of dollars before beginning. It needs credible project preparation that converts renewable potential into evidence, and evidence into investable infrastructure.